We eat, we study, we procrastinate, and we might even be hitting the snooze button 5 times before getting up on a daily basis. This daily mix of emotions and behavior and thoughts that we have are all because of the built in wiring system in our bodies, that is, the nervous system, which communicates at a fleeting speed, like texting. These text messages, or action potentials, are sent out essentially because of changes in the cell membrane permeability. All cells in the body have a membrane potential, a difference in voltage or electrical charge between the inside and the outside of the membrane, basically how positive or negative is the inside of the cell compared to the outside. This difference in voltage due to ion permeability changes can be explained by the Goldman equation, which determines the membrane potential produced by several ions associated with the propagation of an action potential. The most important part of this equation is the permeability values of these different ions, denoted as P. As permeability for different ions change, the membrane potential also changes. In other words, as the concentration of different ions in and out of the cell changes, we are able to depolarize or hyperpolarize the membrane. At rest, there is a high concentration of sodium outside of the cell versus the inside, and a high concentration of potassium ions inside relative to the outside, creating a net negative charge of about negative 65 millivolts. This is called the resting potential. A neuron becomes active when enough stimuli at the dendrites creates a change in the neuron that eventually reaches the axon, creating an action potential. When an action potential begins, voltage-gated sodium ion channels change its conformation due to the change of voltage up to a certain voltage threshold, causing an increase in the permeability of the membrane to sodium ions, and so positive sodium ions are rushed in, such that the inside starts to become less and less negative, thus rapidly depolarizing the membrane. This is called the rising phase. Two strong forces allow for these sodium ions in the cell: the electrical force, which is determined by the voltage difference, and the diffusion force, which is determined by the concentration gradient across the membrane. With the increased depolarization, voltage-gated potassium channels begin to open, but at a much slower rate than the sodium channels, causing potassium ions to flow out of the cell. When the depolarization reaches its peak at about 40 millivolts, sodium channels become refractory, thus non-activable, and an influx of sodium ions is blocked, greatly decreasing permeability to sodium ions. Potassium channels continue to open though, increasing the permeability to potassium ions, allowing more and more of them to leave the cell. Similar to the outflow of sodium, the potassium ions rush down both its concentration and electrochemical gradients to get out of the cell. This leads to a decline in membrane potential in the falling phase, which brings the charge inside of the cell back down to negative relative to the outside. Potassium channels begin to close, but many remain open, allowing the membrane potential to decline below its resting potential in a process called hyperpolarization. When most of the voltage-gated potassium channels have closed, the cell recovers back to its resting potential, allowing for sodium channels to shift from a refractory state to a regular closed state, ready to be activated once again by depolarization. So to review, at the rising phase, the membrane permeability to sodium increases rapidly, and at the peak, it is greatly decreased, while the membrane permeability to potassium increases in the falling phase, up until to a point of hyperpolarization, and then decreases to get the membrane potential back to rest. This is all happening on one tiny little area of the neuron, but this change in voltage creeps over to the next bunch of voltage-sensitive sodium channels, and to the next batch, and so on down the line, eventually reaching the terminals where the signal would be transmitted to the next neuron. So that is how changes in ion permeability allow action potentials to communicate down a cascade of neurons from our peripheral nervous system all the way up to the spinal cord into the brain, and then back out again.